This is another example of a Prince algorithm. The English version time will be written under the video, so you can just check if you prefer the English version. But the beginning of the video is in Tree version. So let's start. Now, Prince algorithm can be on my setting rules or say before you notice that you are done, you need to get all the vertices. Okay, I will say we need all the vertices. That is number one. Number two, your number of edges should be the number of vertices minus one. It is here 1, 2, 3, 4, 5. If we are saying 4 edges, so you have 4 edges, that means you 18. Another one, all nodes should be connected. I was saying you connected. You need to we don't run in a cycle. Untimi nko wachi beam unless that is the last step. Iye video na obeti asi. Now, obechu su baby a person will start it free. In this video, let's start from A. Okay. Now, what's your values in the answer? 2, 3, 5. In now you're connected to A. We will bo A mo. We will bo A mo. We will bo A mo. So these 3 values, they are we initial. So you go here. B. Ube drew B. B were 4 values. 1, 2, 3, 4. 1, 2, 3, 4. Now what is all these values? The initial. Of course, we because we initial. But you could choose we are free A, yes, who free A, young quiet beam. Into Baba be choose we. Neba, Baba be choose we. But I know what we sound who say. Values in a bibo demo, 3 values in a bibo demo. 5 bibo demo, 2 bibo demo, 1 bibo demo. The initial. We initial. Until the can hear no answer. That be the kind consider baby a okono. She values si bibo answer. Na be draw. Oh, be D. 3 value. Do say B angle we initial. But and drawn straight. You do say ye here and no anka sabeba. Say ye here so no be you no free. Ti ye be D. Numbers 3 ni bibo D mo. The initial. We initial. Okay. Good. So say yenya A, B, D, C. Aka F on kwa. Because we nyina we. Very simple. 2 numbers and a bebo F mu. You mean the initial. E to F. Remember, you free F and by E, if E mum ne call F. Okay, good. If you when all the 5 vertices, 5 vertices, you know, are they connected? They all need to be connected. Medical culture. Now, A, B, F, the boom. But aka a kwanya DC no be fast wabo we. Now, you bet him draw from her to her. By the way, 7. You bet him draw from her to her. We 2. You bet him draw from her to her. We 5. It is our 3 values we dey in a yin choose. You bet choose 2 no. Now I'm catching will say we na we here and no one kasa beba. Won say no one kasa ba. But we be say we see you free D you make DB. But me catch you say unless the last step. This is the last step. So we bet him draw from her to her and now from her to her. United the last step here she beam so it will not run in a cycle. You see when you're A, B, C, D, F. I think this is supposed to be E. I don't think it will be F. I don't think it will be F. A, B, C, D, E. Good. When you're all the vertices, before say should be we know also who say when you're all the vertices. And now edges in so I was say yeah the vertex minus 1. You see vertex near 1, 2, 3, 4, 5. Into I was say yeah edge in so yeah 4 because 5 minus 1 is 4. 1, 1, 2, 3, 4. Good. That means we are done. 2 plus 3 is 5. 5 plus 2 is um 7. 7 plus 1 is 8. So the weight is equal to 8. That is all. What do you say? Good. So let's try the English version. Okay. Now, the Prim's algorithm is stating that when you have this, before you can realize that you are done, number one, you have to have the number of vertices. Now forget about this. You have to have the number of vertices. Okay. So even if we have A, B, C, D, and E is not there, that means we are not done. So we have to have the number of vertices. Number two, the edges, the lines should be the number of vertices minus 1. So since we have 1, 2, 3, 4, 5, that means that in our final algorithm, the lines should be 5 minus 1 lines. We should get 4 lines. If you get 3 lines, we are wrong. If you get 7 lines, we are wrong. We should get 5 minus 1 lines. That is 4 lines. Good. All the edges, all the node need to be connected. You need to connect all the node. Even if one is isolated and it is not connected, you are wrong. Good. You don't run in a cycle. You don't run in a cycle. Once you leave a particular node, you don't come back to the node again. You can come and pick a line from the node, or you can only come back to that particular node if that is the last step. You are not going anywhere again. I said you can come and pick a line from that particular node, or you can visit that particular node if that is the last line. Good. So let's do it this way. You have A, B, C, D, E. Good. You choose where you want to start from. In this case, I want to start from D. So I want to start from D. Let's start from D to C is 1. Now, before I continue, it's not that it is obvious I have to go to D to C. There are 3 connections to D: A to D, B to D, and C to D. But among these 3, which one is the least? This one was the least. That is why I chose that part. I should have explained. Good. So this one was the least. That's why I chose that one. Good. Now, once you reach C, C has 2 connections. 1, 2. Among the 2, which one is the least? This one is the least. But Prem says that once you leave a node, you cannot go back. We left D, so we cannot come back to D. So we are forced to go to B. Now, you look at the B critically before you go to B. B has 1, 2, 3, 4. 1, 2, 3, 4. 4 connections. Among these 4 connections, which one is the least? So it's not because you are forced to choose 7, then you go to B. No, don't do that. You look at B and ask yourself, B has 4 connections. 1, 2, 3, 4. Among these 4, which one is the least? The least of them is 2 and 2. But don't choose this one, because if you choose that part, you are coming back to D, which will run back in a cycle. We've already drawn D. So you don't have to choose this part. So you have to choose that part. So you go from B to A. Once you're at A has 2 connections, 3 and D, 3 and 5. Between the 2, which one is the least? 3 is the least. You go there. 3. Here was supposed to be 2. Now, look at something. We have A, B, C, D, E. And Prince was saying that if you have the number of vertices, that means you are almost done. Because at the end of the day, we need to get 5 vertices. We have 1, 2, 3, 4, 5. And I have 1, 2, 3, 4, 5. So that means that we are done. But there was another condition. Another condition is that all of the vertices need to be connected. Right now, are they all connected? This is connected to that. But these two are not connected to this. So we are not done. Prince was saying another thing. In your final algorithm, the number of edges should be the number of vertices minus 1. 1, 2, 3, 4, 5. We have 5 vertices. So that means we need to get 4 lines. But we have 1, 2, 3. So that means we are not done. So now, right now, we are looking for 4 lines. And the 4 lines, we make sure all of them are connected. Now that you are going to look into the whole algorithm to check which of them to be connected to this. Of course, you can connect 5 here. You can connect 7 here. You can connect 2 here. You cannot connect the 4 here. If you connect it, still this is connected and it will not be part of this. So you either connect here, you connect there, or connect there. So among these 3 values, which one of them is the least? This is the least. Now, someone may ask, are we not coming to D? Because he said once we leave D, we cannot come to D. I told you, unless the last step. This is the last step. Unless the last step. So this is the last step. That's why we're able to come to D. So right now we have 1, 2, 3, 4, 4 lines, condition satisfied. 1, 2, 3, 4, 5. 5 vertices, condition satisfied. Are they all connected? Yes, they are all connected. Condition satisfied. Did we use the least values? 1, 2, 2, 3. Yes, we use the least values. Condition satisfied. So the weight of the algorithm is equal to 8. That means we are done. This is Prim's algorithm. So we will look at the Bell-Fulkerson algorithm and the Crusack's algorithm.